Hi, thank you, Marie, for the nice introduction, and thank you for inviting me. Now, hearing my CV read out, I realized it could still mean that I still do theory, but I actually made a transition kind of to the dark side. I left theory after my PhD, and well, towards the end of my PhD, I did some experiments with Richard Cheng at Yale on optical resonance that I before that studied theoretically, and since then, as a postdoc at Max Planck, I basically moved towards the experimental side of it. And what you see here on the front picture is actually a real physical existing resonator that by basically optical dielectric material that is forced by a diamond to get into a round shape. So it is quite mechanical work, quite far away from the idealized theory that I played with as a student. Good, so the type of, so we're moving back basically to the electromagnetic spectrum in my talk. And since I'm interested in nonlinear wave mixing, I need to have rather high field intensities. And to get to high field intensities, I use a resonant system. And the resonators that we choose are these type of whispering gallery mode resonators that are basically just like a standard, or they are different to a standard dielectric resonator where I would have usually a Fabry-Perot resonator where I just have two mirrors, which somehow confine the light in it. But it is difficult if you want to have this at many different wavelengths, and you need specific coatings, and metal mirrors are just not good enough. And so we like the concept of total internal reflection, where you just have some chunk of higher refractive index material, so higher refractive index material inside and lower refractive index material outside. And so I can have total internal reflection at the boundary. And with this, it's 100% reflectivity if the resonator is large enough and I don't have curvature effects. Or if I'm too steep at the angle, then I can get refraction out of it. But when we take a completely round symmetry, I can form these kind of whispering gallery modes. They're called whispering gallery modes due to the acoustic analog, first mathematically described by Lord Rayleigh from the St. Paul's Cathedral, where you have the surface boundary kind of here, which is a convex shape. So if you're standing here and whispering or talking towards the direction of the wall, the sound wave creeps along the wall to the other listener over here, but it doesn't take the direct way across. And so they're creeping waves, and they form in any kind of convex shape that you have. But we try to, doing my PhD, I kind of studied it in a complicated form with lots of mixing of chaotic waves and non-chaotic, or chaotic rays and non-chaotic rays. But moving up to the experimental side, we made them easy and just perfectly round. And if we make them perfectly smooth, we also have very little scattering to deal with. And in such structures, if they are good, we can get confinement of with quality factors of 10 to the 8 to 10 to the 11. And that means that the optical field oscillates 10 to the 8 times before it leaks out of the system. If I make the system rather small, then I get a high finesse, which means I have really high field intensities in the system. If I would compare this to a tuning fork, that would ring for about 10 hours. So these resonators are pretty good, and light stays in there for a very long time. Now, how do we describe that? And I think this is the slide, next slide is the slide that combines most of the work that people do here, because we're basically writing down Maxwell's equation in spherical coordinates, and in particular, the Helmholtz equation, which leads to a wave equation, which is, I guess, the equation that governs most things of our common interest. But I showed you that we have rotationally symmetric structures, and so all we have to do is take this Laplacian here in a spherical coordinates or toroidal coordinates, depending on the geometries we in particular have. Thankfully, this has all been solved long time ago. It makes it much more complicated looking, but the solutions are just what you might expect. There are Bessel functions, Henkel functions, associated Legendre polynomials, and spherical harmonics. And so in particular, when we look at fields inside of my disk resonator, so I don't have a completely sphere, but maybe just a disk, where I can have total internal reflection guiding these waves. I have the back part, this e to the im5 here, and that field distribution really just tells me how many wavelengths of light do I have creeping along the wave. So that's the most standard way, more similar to the Fabric Pro resonator. The next bit there, these associated Legendre polynomials, tell me something about more the polar coordinates to this. So I have some modes that shift upwards to the polar angle, and I can play with them around. And then the inner lying bits, that's a Bessel function here for us, and where we can get higher order modes that are deeper inlying in the resonator. And so in our system, all of these modes exist, and we want to address certain different modes. And especially if you want to have interaction with a number of different fields, it becomes interesting to see how all these different fields overlap. And I'll go more into this later on. Now, how do we get light into this system? If we have total internal reflection, and that's perfect, then we have 100% reflectivity, and the light would never get out of the system. But thankfully, we do have some option to communicate with that system, and that's through the Henkel function here. In a certain way, you can see that there's a little bit of light leaking out of the system. Well, it's an evanescent field. It approximates well to an exponential decay. And so there is a bit of field. It's not propagating, but the field is there. And so if I bring into that vicinity another field, I can have the fields coupled to each other, and again, get some energy transfer happening. The way that we do this, we couple with a prism. So at a prism backside, if I do this correct, I have total internal reflection here. So I have an evanescent field on the backside of the prism. I bring the prism rather close to my optical resonator. And if I do this within the wavelength, I can get coupling to that. And what I would then do is I take my laser, I change its frequency, and depending on if the frequency is consumable to the number of wavelengths in the resonator, I will get light coupled into the resonator. And at that point, if it's coupled critically, if the rates of coupling are the same as the in coupling is the same as the out coupling rates, I get complete dips. So all the light from the laser goes into the resonator and not onto the detector anymore. And with this, I get the spectrum of the resonator that I have under investigation. Here's actually a picture of one of these resonators, which I will be telling you later on more about. And here's a little prism. Give you some ballparks to this typical values. The refractive indices that we deal with in the materials that we use is around 2. They're crystals. Diameters are like, or radius is like 3. Diameters is about 3 millimeters. Typical values, line width is about 1 megahertz. The free spectral range, so the distance between having m number of wavelength and m plus 1 number of wavelength in the resonator is about 15 gigahertz. Quality factor is around 10 to the 8. Finesse about 10,000. So if I have an intrinsic, if I'm interested in how much power is actually inside of that resonator, if I use 1 milliwatt of input power and I couple this critically into the resonator, I get 10.7 watts in it, which is a nice amplification in a certain way. But if I really take it only into the mode volume where the optical light whizzes around, I get around 10 to the 12 watts per square meter. So I have really, really high field intensities. And these high field intensities allow me to harness the nonlinearity of the dielectric material that we use. Some other ways of getting light into the resonator is angle polished fiber. So I have an optical fiber and I just polish it to the side and I can get here kind of a prism effect, or I can take an optical fiber and I taper it. So I remove the cladding and I get really thin, and then I can also couple light into this. Here is a picture which is really hard to see. This is kind of a resonator that we have, and there's a little tiny green thing above that, which is a tapered optical fiber. So you can see this under a microscope. Now, why would you want to go through all of this to make these type of whispering gallery mode resonators? Well, they have a number of benefits. They are monolithic. They have very high Q factors and a really small footprint. And so they have been used quite extensively for sensing applications. We dabbled a little bit in this and trying to measure the salt content of water around it, which you can do pretty precise because you have a long evanescent field in the medium surrounding the resonator, and you can measure changes rather precise. You can rather easily tune them if you have really high quality factors or really narrow line width. Changes in the environment change something. So if you change the temperature, it really nicely tunes, and you can make tunable lasers with this. You have very strong confinement of it, and lots of power in it. So the light is confined, and it actually, the light can form a pressure wave in it, and so you get into the light ringing in a certain way the resonator, and you have optomechanical interactions in these devices. But the main thing that I right now like about them is that you have tunable coupling rates. So the rate with which I can couple into the resonator is variable. So it would be like if you have a Fabry Perot resonator, basically these mirrors, you could change the reflectivity of the mirrors on the fly. And that's usually very difficult. But for us, we just have to change the distance of the prism to the resonator, and we can couple this. And I think the main feature is that we are ultra broadband. Total internal reflection works in any domain where the material is transparent. And so it can be from the visible to the near infrared to the microwave. All of these waves can be confined close to the rim. And if they're confined in the same area, then they can potentially talk and communicate with each other through the nonlinearity of the material. So these are the benefits. Now, how difficult is it to make such resonators? The easiest is basically just using a certain way the element that we've heard the talk before that, water. Just take some spray, some water droplet, and you have a very nice whispering gallery mode resonator. And me scattering is really just scattering of small rain droplets. Now, people start to get a little bit annoyed, have done studies on that, but it's annoying because you don't really keep them in place. And so people have kind of frozen out rain droplets by melting little glass balls and put them on a thread that work quite well. Or they made toroidal resonators where you make something, then you melt it, and surface tension really makes a really, really nice surface. So you don't have to worry about scattering much. The problem is that you are limited to amorphous materials because the reflow is something which just makes the orientation of the material inside random, and so it's amorphous. You get pretty good quality factors, but at maybe around 10 to the 8 in silica. But what we are interested, since I'm interested in nonlinearities and interested in second order nonlinearities, these only really exist in single crystals where you have certain symmetries, or basically where you do not have certain symmetries. So second order nonlinearity only exists in non-inversion symmetric symmetries. And so looking at the way of how to make resonators out of single crystals is an interesting field which people study. And for sure, you can do it with lithography. You have really good, you can do with most materials or nearly any material, and you just use e-beam lithography or some other etching methods, and you can get pretty good shape control to it, and they all look very neat and nice. But if you look at the quality factors that people achieve there, they're somewhat limited. And the main problem is that a crystal has preferred direction in which it wants to go, and crystal is defined by basically having certain directions that are different than others, and that also relates to the mechanical properties of it. And if you etch things, these mechanical properties relate to the chemical properties, so the etching rates are quite different in different directions. So making something that doesn't want to be round, completely round, is somewhat tricky. And so the surface qualities are limited to around 10 to the 7, especially Marco Loncar and a number of people are really, really pushing this and trying to get this quality up. But they are still somewhat limited to another method that we prefer, and that is of diamond turning. And that is based on really brute force. So I take a single point diamond, the hardest material on Earth, to really just push through the system and get a really nice surface quality. I can polish it later on, and then we have really pristine surface, and we have done this to any material that we encountered. We managed to make resonators out of it. We have reasonable shape control, but we just have really great surface quality, limited only by the material itself, only by really the intrinsics losses of that material. And so it's in a certain way the crystal grower's fault and not our fault. Now, what can you do with these systems? And I'll get to my first point to this. It's the idea of frequency up conversion. Now, why, or mixing of microwaves and optical fields in the same resonator. Now, why would you care about this? Well, here we have the spectrum from electronics to photonics, all the same electromagnetic waves. In the photonics area, we have this telecommunication domain, which makes our communication possible right now because we go through optical fibers at 1.5 micrometers, and it's really, really, really a great domain. It's also the domain where studying atomic and ionic resonances is very well established. Quantum optics is strongly in it, and good things, you have rather high energy photons, and so you have good single photon detectors. Now, on the other side, on the electronic side, you have a number of pretty cool things recently developed, these superconducting microwave circuits. So you can actually do now human-made atoms and really have your microwave qubit that reassembles an atom, but you can really control this nicely and can make really large-scale systems out of this. And it's the most likely point which I think is for scalable quantum computers. Google, IBM are really big in this field, and you get to, I think by now, about 100 microwave qubits that all can interact, and so you basically have a very small quantum computer. Now, if you want to have it scalable, you would like to connect a number of these different quantum computers, and here you face a problem that they all need to sit in a cryostat, because you're working with a microwave qubit, and just room temperature or just anything over millikelvin temperatures has spurious microwave photons around, and so they would destroy this whole thing. So you have a scalable thing that only works in one pot. Now, how could you connect different of these quantum computers with each other? Well, the idea is, can we connect just the microwave to the telecom domain coherently? And the idea there is, let's use nonlinear optics. Our ideas is, well, a number of other people have other ideas in mind. So you need a nonlinearity to have different waves interacting. There are very much different ways of doing it. We wrote my postdoc here, Nick Lambert, wrote a review on it, and you can see that many different people in different areas of physics try to achieve the same thing. Our way of doing it is through the nonlinear response of the material, the second order nonlinear response. So that's three-wave mixing. This first part gives you basically the refractive index. This next part is the first nonlinear bit to it. And what you can have if you have a material that has a non-zero chi2 is if you have an optical pump and you have a small microwave photon, you can basically add them up together, and energy needs to be conserved. And so you can get a sideband on the anti-Stokes side, but at the same time, you can also get a down conversion difference frequency generation system. So it's a nonlinear process, so they are rather weak unless you have very high field strength or a good material. So in our system, I say if I have it resonantly enhanced, I have very high field strength, but I need to fulfill the resonant conditions. I need to have a good nonlinear material, but since we can use these single crystals, they are very good, but we need to see how the modes can actually overlap. And that's somewhat non-trivial because we have about 5 orders of magnitude difference in wavelength between the microwave modes and the optical fields to overlap. And so we like to write, which for some in the audience might not seem to be the most sensible way to write the Hamiltonian to this, just looking at the energy of the total system, and in particular only looking at this interaction Hamiltonian where the nonlinear term comes in. Let me just skip over these things. We can quantize this. The main point is I want to show that there are certain, that we come to an equation which shows us about this interaction, but it all depends on how this overlap of the three interacting fields looks like. So just an integral of three waves, in a certain way, or three modes in our system. And since we have whispering gallery modes, we have the rotationally spherical geometry in the system. And we can see if we have three fields being multiplied here being a symmetric function, usually this integral would always be 0 unless this exponent here is 0. If the exponent is 0, then this whole integral can give me a finite value. And this is actually a condition we call an optics phase matching, or it's also just angular momentum conservation. So it gives us a relation between the number of wavelengths of the microwave field and the optical fields that need to interact at the same time while keeping the resonance condition fulfilled. Good, so we have this, and in a system like ours, it looks like that. We have a number of modes in this, and what can happen in the system if they're well separated. If I look at the front term here, it can happen that I have a optical pump photon coming in there, at the same time a microwave photon coming in there that stimulates a down conversion process where I get another photon generated in the down conversion side. Energy needs to be conserved, so this distance needs to be exactly the energy of the microwave photon, and phase matching needs to be also conserved. Good. And that leads to the fact that my microwave field can have only one wavelength to be properly matched to the system. We call this down conversion. It basically entangles microwave and optical photons because they both show up at the same time. It's a parametric amplifier, or we can generate additional microwave photons because in a certain way this microwave photon stimulates it and another microwave photon shows up. So we have suddenly two microwave photons out of the system. But if you really want to do connecting the quantum computer to another system, we don't want to have this process. We want to have the opposite process. The other side, we have an optical photon and a microwave photon, both getting annihilated, and a new photon showing up in the upconverted sideband. Energy conservation is exactly the same. Phase matching is exactly the same. And both, and in this case, we can detect the microwaves. We can cool down microwaves. So if I just have a thing at normal higher temperatures and have spurious microwave photons just thermally excited in there, I can take them out of the system and cool down the microwave modes. Or I can really transduce it. If I have my microwave photon coming from my quantum computer, I can take that, coherently convert it to the optical domain, and then I can, it's the same qubit, it has the same information in it in the optical domain, but I can send it along a fiber and connect to a different system. Good, that's all great, but usually both systems happen at the same time, which is not really that good. And so you need to have means of only getting one of these processes going. You can do this by detuning the system. We rather like to have it by changing the free spectral range on both sides of it, such that they are asymmetric. And I'll just jump slightly over it. That happens in resonators because you have mixing of different polarization of light in it. And so if you see this coupling of different fields, you can get an avoided crossing here, where it results to the fact that you can really get the up conversion versus the down conversion. How does this look in the lab? Well, we need to have a way to confine the microwave field. So we have this metallic cavity in here, and we have a standing electromagnetic wave in here that just oscillates with one wavelength. We put our optical light through a prism in here, and we look at an optical spectrum analyzer to see what happens. These are our three interacting optical fields, and we can now take the light and put light in, put a microwave in at the same time, and see what happens. And so we see here a little side peak coming up and down. So in a certain way, we are transferring microwave radiation into the optical domain. And we can selectively do this on the down converted side and the up converted side. Now, how efficient is this whole process? We've shown that here it is about 0.1% per milliwatt and we want to get to 100% conversion efficiency. So you would just have to go in with 1 watt of power to achieve this. Unfortunately, the materials are so nonlinear that if you try to come with more powers than we put in, they degrade and do all kind of funny stuff that you don't want to have. So you have no good control over it. So it's a problem. And at one point we were leading basically in the electro-optic upconversion bit here. In this review, we compare all kind of people where the trend is. It's still a completely outstanding problem. There are many different ways, but currently the maximum is like at 50%, but with really small bandwidth. So it still will take some time for quantum computers to be fully connected to different domains. So that much you can do with this system. Let me briefly jump over to one other side that you can do with this system, just to give you an idea of it. I mean, I said upconversion is good. I want to have only one sideband here. And I said that, well, having both systems happening at the same time would be really, really terrible because it pollutes the system and you cannot do upconversion. But then we realized, wait a second, sometimes maybe you want to have both sides happening. And if this happens, then you maybe can have to put more power in, because microwave photons in a certain way are cheap unless you want to do this cryogenically. So you can just have a very strong microwave source. And maybe I can get something nice out of it. And that was a frequency comb. So we just took exactly the same system and just pumped lots of microwave photons in it. And we saw some kind of frequency comb. So it's exactly, well, frequency combs are good and useful. It's exactly the same system. We just put way more power in than we thought was sensible. And the output of this whole thing was, yes, we could see a frequency comb with very nice spacing, dependent on the frequency of the microwaves that we put into this, and quite stable. And surprisingly, we can even negotiate the dispersion in the system such that we have a pretty good understanding on how long these frequency combs are and why and when they break off. And we have shown this quite nicely that I don't go over this, how this works. So that's a single electro-optic frequency comb. Now, as a final bit to this, my postdoc right now is working on, or has worked on, dual frequency combs, where you basically want to have two frequency combs out of such a system. And just the trick here is, you remember this integral of G, which had all the three interacting fields in it. It also has a nonlinearity tensor in it. So in crystal, we have this tensor. What we had is that the optical field had a number of oscillations. The two optical fields had a number of oscillations. They're shifted exactly by one here. The microwave field was oscillating, but getting this oscillating microwave field is rather tricky. And so the idea was, let's see if we cannot get the electro-optic coefficient to oscillate. Now that sounds maybe a little far-fetched, but in a crystal, if you orient this against the optic axis, you can actually get this oscillatory behavior in it. And you can do this in a somewhat easier geometry where you have a very tiny ring resonator polished on a system, and you have the magnetic electric field just across from here. And just a conclusion from this is you can get a very nice frequency comb, and you cannot just get one comb, but you get two combs with different or orthogonal polarization. And so you can take them, put them separate, and have one comb as a reference to another comb. And if you do something with this comb, put it to some gas where it absorbs it or something, you can actually get a relative measurement of these two systems and do really good spectroscopy. And these combs are enormously stable because they come out of the same resonator and are really, really, really good. Not completely appreciated by all reviewers, unfortunately. So we've been for a while on archive, but it's getting there. So yes, that's just spectroscopy probe, and let's just jump over it. So with this, I like to just concluding this Let's come to a conclusion. So I showed you that microwave conversion is possible in our type of resonators. If you put more energy in it, you can get a single frequency comb. And we have now also shown dual frequency combs. But all of this work, I mean, you've seen some of my group members here. My group is somewhat larger here in Dunedin. And here's a rather recent photo of my group. And I'd like to acknowledge the different funders, and I'd like to acknowledge you and thank you for your attention. Thank you.
Thank you, Harald. Are there some questions? Oh, yes, I mean, you have a question. Please go ahead.
Yeah, thank you very much, Harald. Actually, I have a question regarding the stability of the frequency comb. And actually, I'm not really familiar with your optical system here, but I was suspecting that you might get modulation and stability, isn't it? Because if you start, or do you have modulation and stability in your system? That's maybe the
I mean, we have our
question.
stability in a certain way. It's different than Kerr combs. Kerr combs are third order nonlinearity, so we have second order nonlinearity, and we put in, I mean, we're putting in two fields. We're putting in our optical field and we put on our microwave field. And so they have a very fixed relation
I see.
to each other. And so especially the relative stability, so the stability of the comb, to get the comb started is easy because I just have it all synchronized to the same clock in the background. And so there is no drifting of the different bits. If the resonator drifts, I would have to stabilize that,
I see.
the temperature to it. But especially if I do the dual comb system, I have both of them coming from exactly the same place. So if I look at the relative phase noise to it, we are at 0.4 millihertz. And so the trick was to basically get all of these things here very stable. And so we took a bucket of sand and put the things in sand, let it sit there for a day, and then things got to the stability that we were interested in.
Okay.
People have done similar things, but in Kerr combs,
it's easy to trigger.
You have all this nonlinearity that it has to just jump into the right place, and then you have to keep it there. You have to tweak it to get there. And some of the reviewers complained that, well, it has been shown. Yes, it has been shown when you have two Menlo systems and a hydrogen maser to stabilize all of this, you can get to these results, but it's coming out of the box, basically. We put the stable signals in and we get a comb. So
that's interesting. Thank you very much. Thanks.
Sure.
Okay, so let's take another question and then we'll go for the breakout rooms. So please, Arena, you can ask a question.
Yeah, I have a question. You mentioned that you can measure the salinity with that. Am I right? So how do you do that?
I can measure the change in salinity.
You can measure the change in salinity. How do you do that?
In the fact that the salinity changes the refractive index of the material. So sensing with these resonators is, many people like to do it because you can be very precise, but you can basically anything that changes, you measure. If it's the door slamming or the pressure of the system changing, the temperature changing. So if you have a very, very well-controlled system, which we had everything stabilized, the temperature stabilized, everything stabilized, and just slowly dripped more salt into it. And so we knew that only one parameter was changing, and we could detect that really, really precisely. So,
but I mean, in terms on physics, do you actually measure? Yeah.
Okay. So what I measure in physics, we looked at our resonance, basically the position of the resonance, where it was, and so that the real resonance. If I have here a picture of my my fields. Sorry, where are my fields? So that strongly, basically, the position where the resonance is strongly depends on all the parameters, the refractive index inside and also the refractive index outside. And since I have a very, very narrow resonance, a very small line width, if I get a fractional change of like 10 to the -4 to 10 to -5 in refractive index, I can measure that. And that's what exactly we did. So we had some salt and solution, and we slowly increased the concentration, and that changed the refractive index by the 4th digit. And we could see.
So basically, you're measuring the salinity changes directly, so with no kind of in-between steps.
Yes.
Like
We measure-
directly.
we measure changes directly.